To analyze the forces acting on an object on an incline, I say that we resolve all forces, and I think I'm misusing the word resolve here. Resolve really means find the resultant of, which would correspond more to putting the components together into the resultant vector than to breaking the vector apart. I might better say we break all forces into their components parallel and perpendicular to the incline. Now the important thing is we look at the components parallel and perpendicular to the incline, and we apply the conditions of equilibrium. Now, the first condition of equilibrium that holds on an incline is that the sum of the y forces is 0, because y is the direction perpendicular to the incline. If the incline is strong enough to support the object, that is, to apply the elastic normal force without exceeding its elastic limit, which is an implicit assumption, then we have y equilibrium. The object doesn't come off of the incline. Well, actually, I guess we could be lifting up with a force and get the object to come off the incline, but that's not really an incline problem. If the object comes off the incline, we no longer care about what happens in the incline because we immediately leave it. Okay, but anyhow, we have y equilibrium, and that usually tells us, for example, that if there aren't any other forces perpendicular to the incline, that the normal force will be equal and opposite to the gravitational component perpendicular to the incline. In any case, if the object stays in the incline, this is always the case. Now, we might or might not have x equilibrium. For example, we know that things can rest on inclines as long as we have a little bit of friction and not too big of an angle, so that we have a sum of the x forces being 0. Or we can have an object moving with constant velocity up or down an incline. We've attempted to achieve that in several lab exercises. So we might or might not have the sum of the x forces equal to 0. But we always test. We always keep in mind that it's possible that we do, and we check to see whether we do. We look at the sum of the x forces and decide whether we do have equilibrium. The question here is, why do we say that for small angles, for small slopes, the acceleration of an object down an incline seems to be proportional to the slope? Well, let's look at the forces. Consistent with what we just did before, we break the, or what we just said before, we break the weight into its components perpendicular and parallel to the incline, and these should be familiar. Okay, we assume no other force is acting. The object is rolling freely down the incline, so the normal force will be equal and opposite to the weight, and we'll have some frictional force, which is mu, the coefficient of friction, times the normal force, which is mg cosine theta. So we have friction here, and the object accelerates as long as we have enough of an angle that mg sine theta is greater than mu mg cosine theta. So then we have an acceleration down the incline. The acceleration in this case is negative mg sine theta plus mu mg cosine theta. Again, provided theta is big enough that this number is bigger than this number. Otherwise, to digress a minute, the force really isn't equal to this. It'll be less than this, and it'll be at most equal to mg sine theta. For small angle, now, let's consider what this thing means. For small angle, the hypotenuse is pretty close to this distance, which means the hypotenuse is close to the run. I'm trying to move over to slope units here, okay, or the idea of slope. The rise, of course, is whatever it is, but the rise is going to be the hypotenuse times the sine of theta. Okay, well, let's just see. We've got this sine theta and cosine theta. Let's see what kind of approximations we can make for small angle, where the rise, or the hypotenuse and the run are approximately equal. If the hypotenuse and the run don't differ by much, then the sine of the angle, which is rise over hypotenuse, is pretty close to the rise over the run, which is a slope. So that this sine theta here can be replaced by slope, as we've done down here. The cosine, which is run over hypotenuse, well, it's pretty close to run over run, which is just 1. So the cosine of theta up here will be replaced by 1. So we have this relationship. Okay, why is acceleration? Now, I said a minute ago proportional to the slope. I think the statement is a linear function of the slope. Okay? Oh, this is a linear function of the slope. It's some number times the slope plus some other number. This is just a number, and what we've got out in front of slope is just a number. So this is a linear function. A is a linear function of the slope. And for every increase of the slope, the increase in the acceleration is proportional to that slope increase. Still in the context of an incline, how do we observe changes of potential and kinetic energies on an incline? Well, when an object changes its position on an incline, goes either up or down, its potential energy changes, either increases or decreases, depending whether we go up or down. We can measure that by observing the velocities at the two positions. Well, we can measure the kinetic energies, the kinetic energy change at the two positions. And so we can see whether the change of kinetic and the change of potential energy is 0 and actually test this idea of conservation of momentum. Now, if we can get friction down to where it's practically non-existent, we can get a very good test, and these changes will very nearly add up to 0. Okay? Calculating potential energy change by the mass and the vertical change of position, the kinetic energy change by the change in velocity and the mass. We get this. Now, if there's friction in the system, then we're doing some work, delta W, by the system, and that delta W is positive. If there's friction, we got to do work against it. We got to do positive work against friction. And when we do that, then we'll note that that's because the force that we exert against friction is parallel to our motion. So if we're the object, we're doing work against friction, work in the direction. We're exerting a force against friction that's in the direction of our motion, so our delta W is positive. In this case, delta KE plus delta PE plus delta W has to equal 0. This means that if we have a negative change of potential energy going down an incline, for example, we'll have a positive change in kinetic, but some of that negative change of potential is also balanced by the work done, which means that our kinetic energy change is less. Friction prevents us from going as fast down the incline, so that more delta W implies less delta KE.